In this series of videos, you're going to learn about the importance of securing your software and how you can use fuzz testing to locate unknown vulnerabilities before your adversaries do. Before we start, let's take a step back and set the landscape, and better understand the role that software, robustness, and security play in the world that we live in today. Secure software creates new possibilities. New businesses today that did not exist before the creation of this software allow us to share cars, share homes, stream from home, work from home, and arrange same-day home delivery. Of course, these new business possibilities require more software code. How much more code? Today, there are millions of lines of code in just about everything that we use. And it's been estimated that there is now 111 billion new lines of software code being added every year. That means there's the potential for 111 billion new software vulnerabilities to be introduced each year. And it's not just one set of software that we depend on. Today, there's a growing interdependence among individual devices, and they all require unique software. So it's not just one device and one piece of software, but an ever-increasing interconnection of softwares. For example, the smart TV uses software to entertain your family, and that smart TV relies on internet connectivity software. And that runs on a power grid software which is supplied by a power plant software. And power plants are fueled by trucks and trains that use software for delivery. With all of these interdependencies, that means the stakes are rising for software reliability and quality. And it raises a very important question. What if just one piece of software fails? Failure is not something we like to talk about, but given all the interdependencies, it is very important that we address software failure. Although the software industry is over 50 years old, it still produces an unusually high rate of failure. At one point, having your desktop computer crash was annoying. Today, however, the consequences of interconnected software failures are more far-reaching, and they range from the inconvenient to, in some cases, the life-threatening. However, the reliability and quality of software cannot be solely blamed on programmers. In general, even the best programmers will occasionally make mistakes. Rather, it's the process that surrounds those programmers that needs to improve, namely the tools and processes that they use in developing the software. And it is increasingly more critical that we focus on this problem. Why? If we don't identify the software vulnerabilities ourselves, someone else will. Perhaps because of these software interdependencies, adversaries have emerged to take advantage of the vulnerabilities. Despite what you see in the movies, real-life criminal hacking isn't somebody wearing a black hoodie in a room full of monitors. In real life, the adversaries are typically average people who take atypical steps in trying to compromise your network. They have a wide range of skill sets and motivations. These include a casual attacker is just interested in the challenge or the thrill of the chase. Think of them as graffiti artists or common street punks causing damage along the way. Hacktivists and political groups have other types of agenda. Often they cause software failures through denial-of-service attacks in order to make a point. Organized crime is in it for the money. Often they use ransomware to extort the victim into paying for the decryption of their own data. And finally, nation-state interests. These are either military or political. They can steal sensitive data through espionage, or they can attempt to shut down hospitals and power grids to paralyze society. One thing all of these different adversaries have in common is that they find and exploit software vulnerabilities, sometimes unknown vulnerabilities. The real enemies then are not the programmers and not even the adversaries, but the software bugs or vulnerabilities themselves. Let's take a look at how a typical adversarial attack occurs. Behind those big attacks that you read about in the news, there's a lot of time and effort that goes into preparing. An adversary will most likely start by spending time mapping out everything that's running on your network. This includes all the interconnected mobile phones, laptops, printers, and desktops used, in addition to all the servers and cloud instances. This attacker will want to know every piece of equipment and every piece of software running on that equipment. Basically, every place where there's a piece of software taking in some kind of input, either from a user or from another system, that is a place where an attacker could potentially find an exploitable flaw. If you sum that up, that's the attack surface. And in our ever-increasing interconnected world, our attack surfaces are getting infinitely larger. For example, some organizations are tying ancillary things such as HVAC systems into their organization's network. That's how the data breach at Target occurred. The attackers entered through a third-party HVAC system, and because their network wasn't properly segmented, the adversaries got to the customer credit cards. So if it runs on software and it's got vulnerabilities, it's going to be an attractive target for any adversary. And that's why organizations need to secure their software before the adversaries can attack. First, it's important to understand that with security, there is no 100%. Frankly, it is impossible to secure everything all the time. So more often than not, we're just putting obstacles in front of an adversary so they'll go elsewhere. That's not defeatist, that's reality. What you're really trying to do is balance the value of what you're trying to protect against the effort required to compromise it. Let's say you want to defend your house. You put locks on your doors, but they can be defeated. What about the windows? Someone can smash a window and still get inside. Maybe you put a security system in place, but are there blind spots? Short of erecting a high wall, there's always a way for a determined adversary to break into your house. It's just a question of how hard it is to do so, and how many barriers you feel comfortable putting in place. The situation with software is similar. You can't realistically fix all the software vulnerabilities, but you can find and fix the vulnerabilities yourself to put more barriers between you and your adversary. Today, software is assembled, not written. Meaning, software developers are more likely to stitch together other people's code than write it themselves. This is what gives us the rich features that we've come to expect. You can think about it this way. Software applications are constructed in a way very similar to automobiles. Individual components are sourced from multiple vendors that, when stitched together, produce the final software that is released to the customer. Software applications today contain hundreds of code components that come from a variety of sources. And it's estimated that 85% of modern applications are made up of some third-party code components. That includes free and open source software or commercial off-the-shelf software developed by an external individual or organization. It's not out of laziness that third-party code is used. In fact, there are a variety of benefits to using third-party components. Using third-party components gives developers the boost they need to keep pace with the increasing development speeds. And outsourcing parts of your product to the experts often results in a higher quality output. So if your organization wants to use TLS protocol for securing sensitive communications, it's faster and more secure to use established third-party components such as OpenSSL. Open source software can be free of licensing. This allows developers to release faster without having to code features from scratch or pay for it. So open source code fulfills the criteria that must be met for them to effectively complete their work. But it is folly to think that open source or even consumer off-the-shelf components are not without their own vulnerabilities. Software vulnerabilities can be inherited through your software supply chain, and that's way more common than we'd like to admit. Since 2014, the National Vulnerability Database has reported more than 6,000 new open-source vulnerabilities. Part of that is a result of an active effort to retroactively test and secure open-source products. That's third-party vulnerabilities. What about code vulnerabilities that you and not the third party introduce? Unfortunately, even primary code can suffer from vulnerabilities. Let's talk more about code vulnerabilities. Overall, code vulnerabilities can be divided into 3 distinct groups. Known knowns are code vulnerabilities that are widely known to everyone in the industry. Usually, though, if you hear about a known vulnerability, it has a CVE number associated with it. These are things that reactive tools can look for. Known unknowns are where we recognize the general shape of a vulnerability, but haven't found it yet in the code. So some of it is known, but a lot of it is not. This, of course, requires access to the source code. Known knowns and unknown knowns are easier to defend against because at least some part of it is known. A third type, unknown unknowns, is therefore much more dangerous because almost nothing is known about these vulnerabilities. These unknown vulnerabilities are also called 0 days because the vendor has had 0 days to guard against it. If an adversary or other malicious person finds an unknown vulnerability and develops an exploit for it first, then by definition, no one has any defense against it. On the other hand, had the same vulnerability been caught and found by the internal software development QA testing team, it could have been fixed before release, and the 0 day would not have become an issue. Now that you have some idea of the importance of security and software today, with fuzz testing you should be able to find 0-day vulnerabilities that are lurking inside your software, and therefore defend it against adversaries. In the next video, we'll talk more in depth about fuzz testing.